So once we convert a cripple wall into a shear wall with plywood and bolts and shear transfer ties, it will resist, the earthquake forces, the lateral forces that are caused by earthquakes. But at the same time, there's a force that tries to flip it over, and that's called an overturning force. And we're going to go over overturning forces right now and how they are resisted with hold downs. So it should be pretty obvious what's going on here. The earthquake force is pushing here on the upper top plate, which is nailed into the plywood right here. And when that happens, the shear wall, it just tries to flip over like that. And notice how when it tries to flip up this way, there's a counter force that's provided by the weight that's on this 2x4. And so this right here, that is the overturning that's pushing up on it, and this force down right here, that is the compression. So you'll see that in the entire shear wall. So let's go over this again. So when it overturns, it comes this way, and down when it goes that way, that's called compression. And when it goes up that way, that's called overturning. And then there's a compression force that's also provided by the weight on the 2x4. So that's what happens in every shear wall. It could be 2 inches tall, it could be 20 feet tall. It doesn't matter. They all have to resist overturning. Now, when they're very short, it's not a big deal. When they're tall, it's very, very significant, and we're going to go over that right now. So this is what happens when a shear wall is subjected to overturning forces. Earthquake force comes along here through the floor into the upper top plate, into these nails right here. But the big issue is it's going to want to go like that. It rotates. And when it does, it pushes down on the 2x4 stud right here. That's called compression. And then it also will push up on this one. That's called overturning or tension. And look and see what happened to the bottom of the plywood right here. So all these nails, these little dots, dot, 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 all these different dots, that represents nails. And the plywood just simply tore out. So that's the big issue. Now this actually doesn't happen nearly as much as you would think, and the reason for that is because right up in here, the shear wall, when it's overturning, it has to pick up the wall and the floor, basically pick up the house at the same time, and there's a lot of weight there. So I personally don't think it's that big of a deal. I could be very wrong. Someone, if you have some evidence to prove me wrong, I'd like to hear it. But that's why we put in hold downs. We put them in all the time, which resists this force. But I would, if there's any sort of a doubt or that it's going to be super expensive to do, that would be one of the things I would think about less than bolts and shear transfer ties and good nailing. So here's an example of some damage that was caused by overturning forces. This right here is not plywood, it's called OSB, but it performs and does the exact same thing. And as you can see, the plywood or the OSB pulled up away from the mud sill. That's right here. And so it used to be this nail, used to go right through where this hole is. It used to be nailed into this mud sill, be a nail right here, a nail right here, and a nail right here. And this piece of plywood pulled up away from the framing exactly as it did right here. So this is a visual example of what happened in an actual test. Now another type of damage, though it is not nearly as common, is cross-grain bending damage. So this is the exact same case where this end stud, it pulled up. We had our overturning force right here. It pulled up on the OSB plywood, which then in turn pulled up on this mud sill, and it caused it to split right here. That is called cross-grain bending. So that's another failure mode that we need to be concerned with. This is also corrected with plate washers and bolts, which are discussed elsewhere on the website. So the way we correct this is by installing something called hold downs. So we put a hold down on each end. We'll have a hold down right here, and then we'll have a hold down right here, and then of course we have our bolts and our plywood nailing everywhere else. So I'll show you exactly how these hold downs work. So earthquake force is coming here. It's trying to overturn the shear wall, and as it tries to overturn like that, it causes the overturning force or the tension along this 2x4 right here. Now this 2x4 has this piece of metal called the hold down, and it's been bolted into the 2x4 in this direction like that. And then at the same time, this hold down has been embedded into the concrete with very, very strong epoxy. Now, epoxy basically is glued to the concrete. So now when it tries to pull up, it has to pull up on that mass of concrete, and that's what keeps it from dislodging, coming loose, and prevents the overturning. So this will give you a good idea of how it works. Here's the hold down hardware, and this is the end stud. So this is at the very end of our shear wall. And so this right here, this hold down has been bolted into the end stud. And when the earthquake force hits, it's going to pull up like that as it tries to overturn. And then it's going to pull up against this hold down. And the really critical thing here is we see this bolt is embedded deep into the concrete. That right here is some epoxy that spilled over. And this is going about 16 to 18 inches deep into the concrete, and it's glued in with epoxy, and it's an extremely strong connection there. The failure does not occur in the epoxy. If anything, it's going to be the concrete that cracks, and we're going to discuss that in a minute. So you're going to see one hold down on each end. You'll see one over here, and then you'll see one over on the far end, just like we saw right here. And so as you can see, you see again, it's trying to overturn like that, and it pulls up on the hold down, and it pulls up on the bolt, and then that puts all the concrete under a lot of tension. But the concrete, if it's in any kind of good condition at all, it can withstand that just fine. If for some reason we're working on a very valuable building, for example, a historic building, where they really want to keep damage to an absolute minimum, we will actually put a new concrete underneath the hold down. So here you can see this is the principle. So right here you'll see there's our shear wall, and what we've done is we poured a massive amount of concrete, 3 feet by 3 feet by 3 feet. I think that's almost that is a cubic yard. That's a lot of concrete. So we put a concrete here on this end, concrete here at this end, put in the hold downs, they help our shear wall. And now when the earthquake force, it pulls up this way, it pulls up on this massive amount of concrete, which weighs a lot. I can't remember exactly how much, but it's, thousands of pounds. And this is what it looks like right here. So we had to dig out underneath. We dug out a 3 by 3 by 3, hole, filled it up full of concrete. And before we did that, we put our hold down rod right there. And so when it was all done, it looked like this. Now, again, this is very rare that we'll do this, and it will only be if someone really got a lot of money and they go, man, I just want to make sure I'm 100% bulletproof, and I don't want any movement in my house. Or if it's a a historic building, you really want to, you just really don't want to see any broken glass or anything for something that you really need to preserve. So right now I'm going to go over the mechanics of a shear wall so I can show you how overturning forces are created. Here at the top of this example, we have 3,600 pounds of shear force is being applied along the top of the wall. And this wall happens to be 12 feet long. Now if we take 3,600 pounds of shear force and we divide it by 12, we end up with 300 pounds per linear foot. So that means each linear foot of this shear wall is going to be resisting 300 pounds of force. So we take that 300 pounds, and it's very interesting because from here on, every side of the shear wall will have 300 pounds per linear foot of force applied to it. So, for example, on the right-hand side, it's 8 feet tall, so that means it basically is 8 feet long. We multiply that times 300, so 8 times 300 gives us 2,400 pounds of compression. Now, if we go to the bottom, it's just like the top. We take it's 12 linear feet long. We take that 12 linear feet, we multiply that times 300, and then we end up with 3,600 pounds of shear force along the bottom of the wall. Now that has to be resisted by the bolts. And so we need to put in enough bolts to resist that amount of force. The bolts are actually a counterforce to the shear force that's at the top of the wall. And finally, on the left-hand side, the exact same thing is 8 feet tall. So we take that 8 feet, we multiply it by 300, and we end up with 2,400 pounds of overturning. Now the overturning is what damages the walls. So we need to make sure that we put hardware in, called hold down hardware, on that side of the shear wall to prevent that from happening. Now, please note that, when there's, this has to pick up an entire house. So you might have 2,400 pounds of earthquake force overturning, but it doesn't mean that the shear wall is going to flip over. It's got to pick up an entire house or a portion of a house in order to do that. So that's part of the mechanics of a shear wall in seismic retrofitting. So here's a good example of why tall, narrow shear walls can be a problem. Not just shear walls, but any wall that's tall and narrow. So in this garage, you can see how on the right and left-hand sides we have walls that are, they're probably, 18 inches or so wide and 8 feet tall. And so they've got all the characteristics of a wall that's, can have problems. Now on the right-hand side, we have 3,600 pounds of force, and let's say we're applying that force to the top of the garage wall on the right-hand side, and it's going to want to tip over, because remember we said that, let's say there's 3,600 pounds, there's going to be 43,200 pounds of overturning force that's going to try to knock it over, and you can see where it happened. So this, right in here where that arrow is, that's where it just, pulled up and could not be recovered. So if you can imagine that there is an entire house above this, or, it's a living area above a garage, or, something like that, you can have some real problems unless you do something about it. In some seismic retrofits, we do need narrow, tall walls in order to complete our retrofit in an effective way. And in these cases, we must use something that's made by the companies Simpson Strong-Tie or Hardy Frame. And in these companies, they make special shear walls that are quite narrow, and they can also be fairly tall. So here's an example of one. So here you can see right here, this is a massive hold down. So it can resist a tremendous amount of force, just unbelievable how much force it can resist in terms of overturning. Now this hold down, there's the rod that goes at the base, at the bottom, and it goes down into a massive amount of concrete. You can't see the concrete right here, it's underneath this concrete slab, but it is a massive amount of concrete. So even though this looks like, okay, and I've seen this, sometimes people just put one in their garage and say, oh, I've retrofitted my house with this narrow shear wall. But if you don't put in the concrete work, it simply can't resist the overturning. So that is absolutely critical, that the foundation work, and an engineer has to figure out how much of that there should be. So, and then we can see the hold down over here on the other side. So that's doing the example, just like the things we saw, where one's in compression, one's in uplift at all times. So this is pretty much the only solution we have if we have a very narrow, we need to put in a narrow shear wall. There's some other systems using steel, but we'll look at those in a different section. So let's go ahead and see what happens when a shear wall is short and wide. So just like in the other example, we have 3,600 pounds of earthquake force is being applied to the top of the wall. In this case, it's being resisted by the top of the wall. And so what we do, just like before, we take the 3,600 pounds, we divide it by the 12 linear feet of wall, and that gives us 300 pounds is being resisted by each linear foot of the wall. And that tells us that along the entire wall, there's going to be 300 pounds being resisted on each side. So on the right-hand side, the shear wall is 1 foot tall. So if it resists 300 pounds per linear foot, there's 1 foot there. That means we're going to have 300 pounds of compression. Now on the bottom, it's just like at the top. We have 3,600 pounds is being applied in a counterforce way, and it will be divided by 12, just like at the top, and we have 300 pounds that needs to be resisted by each linear foot. Now that resistance is provided by the bolts, and so we just need to put in enough bolts to resist that 3,600 pounds, and we will have prevented it from moving and provided the counterforce that we need to provide. Now on the left-hand side, we have, again, we have 300 pounds times, the height of the wall, which happens to be 1 foot. So we take the 300 pounds per linear foot, we happen to have 1 foot, and that means we have 300 pounds of overturning. Now 300 pounds of overturning is hardly, it doesn't even need to be resisted. There's enough weight of the house, there's the house, a roof, the floors, the walls, everything. There's a lot of weight on top of that, so you really don't need to do anything. So these are the two examples. On the one side, you have, if they're wide and they're short, overturning is not really a big consideration. But if they're narrow and tall, it's a big consideration. And so one of the tricks of seismic retrofitting is figuring out at what point do you need to put in a hold down. So here's a case where a hold down was put in and it was absolutely unnecessary. Here's this hold down right here. And then if you were to come down this way, probably 8, 10, maybe 12 feet, you would find another hold down. And this, this cripple wall, the hold down itself is 9 inches tall. The cripple wall is probably 12 inches tall. And the overturning, though it will be there, as for all shear walls, it is just so insignificant that it just was not worth addressing. So this, this is a very, very short and wide, long cripple wall. And when it tries to overturn, it's going to have to pick up, a lot of house weight up above it. So let's say we have 300 pounds of overturning force, has to, resist 10,000 pounds of weight from the house. There's absolutely no reason this is necessary. This is very expensive. And you could probably make some kind of case for putting it in, because every single shear wall does have an overturning capacity. But just because it has an overturning component doesn't mean you have to do something about it. So this is a case where it was a real waste of money. And so anyway, we see a lot of engineers, a lot of contractors do this with, for really reasons that I can't understand, except they're doing it from a state of just not knowing any better. Right now we're going to see a test that was done by the Simpson Strong-Tie Company. That's the manufacturer of the Holdowns. And it is going to show you the damage that is caused by overturning forces. Please note that there are no Holdowns here. This is to show you the kind of damage that occurs when there are no Holdowns. I would like to point out that the shear walls did not have hold downs and there was very little weight on top of them. And so in my opinion, the damage was actually quite minimal. I mean, the structure above did not fall down. And if there had been weight up above, the amount of overturning, and certainly the damage caused by overturning, would have been minimal, at least according to this test. Now, there are other tests that I believe were done with much higher loads. In other words, the seismic resistance or the lateral forces they had to resist was much, much higher, which is what caused that damage. So anyway, if anyone has any movie or videos, photographs, anything at all that shows the actual collapse of a building because of overturning force, failure, please let me know, because based on what I can see right now, it does not seem to be that big of an issue. So what I'm going to show you right now is something that's very important in shear wall design, especially when hold downs are involved. A lot of contractors don't understand this. We see a lot of jobs when we tear out plywood where they just don't do it correctly, and it's very important. So please pay attention here. So here we have the earthquake force coming this way, and we have two panels that are right next to each other. There's a seam that's right here. And so what's happening, this panel is overturning and it's putting this in compression. You see how it's pushing down? This one is overturning and it's putting this one in tension or overturning. So what happens is it can come apart right across here. So here you can see how this happens. So this one is overturning like this, creating the compression right here. This one is overturning, creating the tension, and it puts a lot of stress right here. You can see how that can happen. So if these aren't well connected, you can get big trouble where the shear walls come apart. So the force that's coming this way, the nailing basically has to equal the overturning force. So if this is overturning, say with, I don't know, 2,000 pounds of force, we need to put enough nails in to resist that amount of force. So here we see again, this is with hold down. So this green, L-shaped thing, that's a hold down. That's a hold down. And this is, this is coming down, putting in the compression. This is going around, putting in the tension. And that's what those arrows are. Here we have the compression, here we have the tension, and they stay apart. They stay together because this has been properly nailed, so they're well connected. Now, if you put a hole down here, and you put a hole down here, but you don't connect this edge of the plywood to this edge of the plywood, then they're going to come apart right here. And obviously that's something that's very serious. It can cause the shear wall, to fail. I mean, certainly there's no point in putting two pieces of plywood there if the hold downs at this point are just there's no point to have them at all. So let's see what it actually, here's a photograph of what that looks like. So you can see here's a stud right here, here's a stud right here. So this is a double stud, which is what you would normally do right here. So this edge of this plywood would be nailed to one stud. Edge of this plywood be nailed to one, stud. The stud is a 2x4 if you don't know what that is. And so what's happened is the plywood has pulled away, and you can see it's at an angle. See how that nail is at an angle? It's pulling up and away from the stud, and that's the thing that we're worried about. So anyway, this is something, if you're a contractor, if you're a designer, make sure that you put enough nail. It's called stitch nailing. And the best way to figure it out is if you're putting in your plywood nails at 3 inches on center, go ahead and put your 16s or your 12s or 10s or whatever it is at the same spacing, so 3 inches on center. Now when you go into the flat side of the 2x4, this is the wide edge or the flat edge. Well, this is actually called the wide face. This right here is called the narrow face. When you go into the wide face, you have to worry about splitting, so make sure you stagger the nails as shown here. So this is a critical connection, as you can see, and it's one of the things that we see missed all the time. And when I look at a house to see how, what the existing work looks like, unfortunately, I can't see behind the plywood to see if it was done properly. What I normally do is I just check and see the quality of the work, see if the person understood, basic retrofit engineering, and then I make some assumptions. I could cut the plywood out and take a look, but that's not something I do. So for example, this connection is not even addressed in Standard Plan A. That's one of the retrofit guidelines, nor is it in Appendix Chapter A3, which are some very serious oversights. So anyway, in your own jobs, always make sure that this connection is well done. It's very critical, and something a lot of people don't do or understand. So this drawing will show you exactly how stitch nailing is supposed to be done to keep the two 2x4s together and the shear wall that has hold downs from failing. So first, let's look at this. This green right here is one piece of plywood. The red over here represents another piece of plywood. And the red piece is nailed right here along this stud. And the green piece of plywood is nailed right against this stud. And again, we don't want the two to come apart when the overturning occurs. So what we do, each one of those black lines right here and here and here and here, those are all face nails. And a face nail is one that goes into the face of the wide edge of a 2x4. So these face nails go in and they connect these two 2x4s together. So that's all we need to do. And when you do this, you just want to make sure that the nails are put in at the same spacing as your plywood nailing. So for example, if you're nailing your plywood at 3 inches on center, and that means 3 inches apart along all the edges, The edges are really the only part that's really matter anyway. But so anyway, you put them at 3 inches apart on the plywood, then you put your stitch nailing also 3 inches apart. And it's really critical to remember that the wide face of a 2x4 can split easily, so make sure you stagger it. So this right here will keep those, keep that disconnect that we just saw from happening. Now notice this one also has hold downs. So here's our hold down right here, and then we have the hold down right here. And we have the exact same thing. We have the stitch nailing. So we have stitch nailing all the way up this one, and then we have stitch nailing all the way up this one. And that stitch nailing is also the same that we use for the plywood and our other stitch nailing. And the manufacturers of the hold downs, the Simpson, Strong-Tie, the tests they all did were with double hold downs that were nailed just like this. So that's why it's so important to do. Anyway, this right here is a really well built shear wall. Hold downs are in, stitch nailing is done, and this was not there to represent the plywood nailing. You don't see any nails here on the face. You don't see, it doesn't represent plywood at all. So anyway, that's very intentional, just so you can, it's just an illustration of framing and framing only. So here's a photograph that shows you all the hardware and the framing that goes behind a piece of plywood for a shear wall. So right here, this is a bolt, this is a bolt, this is a bolt, this is a bolt, and right here we have the hold down, and then we have a hold down over here. Remember, hold downs always work in pairs. And then right here we have a double stud. This is one right here, and then this one's kind of dark, so you can't see it right here. And these will be nailed right here. These, the two 2x4s will be nailed together at the same schedule, or the nails will be as far apart, the same as the plywood. So usually we do 3 inches on center. So when the plywood goes up, you'll see nails up here at 3 inches on center. You'll see nailing like this at 3 inches on center with the larger nails, usually 16s, or it could be 10s, could be 12s. It doesn't really matter all that much. Now right here, this is where the two pieces of plywood are going to come together. So we're going to have a piece of plywood that's right in here. So from this stud over, it will be a piece of plywood. And then from this stud over, there will be a piece of plywood. So what we're going to do is we're going to stitch nail these together. So we just talked about that. Then we'll put our piece of plywood on, and we're going to nail it here on this 2x4, come up here, nail it up here. You can't see the 2x4 up there. And then it'll come down here on this 2x4, and then of course into the mud sill right here where the bolts are. And then we'll do the exact same thing on this side. So the plywood will be from here to here where the double studs are, and it'll be nailed around all the edges. So it'll be nailed here and then here. And in this case, you can stagger the nails, and the way that would work is if you're doing them 3 inches on center, you would do one right here, come over here, do 3 inches, come over here, do 3 inches. 3 inches apart. So we come up 3 inches, put a nail here, come up 3 inches, put a nail here, come up 3 inches, put a nail here, and that's how you nail into the studs. Now this double stud is set up such that you have the double, you have the nailing, the stitch nailing between the two studs that the hold down is attached to. So that's pretty much how, this is a photograph of how a shear wall is framed that has hold downs. And this is just, basic shear wall design. And just always make sure that you do them like this. And I do want to point out that you see how close the bolts are. They're about every 2 feet, and in new construction they make them so they're every 6 feet. But in retrofit, the way it works is all the earthquake force is going to go into our shear wall. And if our shear wall has been designed to say resist, we figure 550 pounds per square foot, per linear foot, and it's 10 feet long, we would divide the 550, we multiply that by 10, so that's 5,500. And then let's say our bolts can resist 1,000 pounds each, and we'd end up with 5.5 bolts. And then we would actually put 6 in, and we would only do them where the shear wall is. So we wouldn't put them outside the shear wall, just where the plywood is, because all the force goes into the plywood, and that's the only time. That's the only place the bolts are going to do anything. So there's no point in putting any bolts anywhere else. So right now we're going to go over all the components of a retrofit shear wall. There are a lot of components, and it's important to know that if any of them are missing, you're only as strong as your weakest link. So, please look at this very carefully if you have to be doing this yourself, or especially if you're interviewing contractors, you want to make sure that they have an understanding of these components and you have an understanding of how, a shear wall should be built. So the first thing we notice is these hold downs. So we have a hold down on this end, and we have a hold down on this end. We always need to be in pairs. Right here we have the hold down bolt. These usually go down about 16, maybe 14 inches, go in real deep, and then we epoxy them into the concrete. So we have a hold down bolt right here, and then we have a hold down bolt right here. And here's our anchor bolts. Here's an anchor bolt here, an anchor bolt here, an anchor bolt here. And this is, even though they're slightly outside the shear wall, normally we like to put them right inside the shear wall. This one probably was already there and also looked pretty good, so we went ahead and put one there. Now it's important to note that the bolts only do work if they're attached to the shear wall, or if they're attached to the mud sill that the shear wall is nailed to. So what will happen right here is the earthquake force will push, like this onto the mud sill, and then that movement will come here. It'll be restrained by the hold down bolt, in this direction. And some people actually don't even put in, they just figure the hold down bolt's as good as any bolt, and there's no reason to do anything else. And then some people think that a hold down bolt should just be used for what it's made for, which is to resist overturning, and there's no reason to use it for to resist lateral forces. We always, we just figure it's there for, to do one thing, and, putting in bolts is actually pretty easy. So we just go ahead and count, put in the right number of bolts. So anyway, the mud sill will, it'll go this way, it'll push this way, it'll go into this bolt, it'll go into this bolt, it'll go into this bolt, it'll go into this hold down bolt, it'll go into this bolt. And as said previously, we just want to put in enough bolts that the capacity of the bolts equals the capacity of the shear wall. There's no reason to put more bolts in than that. If you do, they're strictly decorative. Now, right here, I'd like to point out that the plywood, we have a piece of plywood here, and we have a piece of plywood here. This piece of plywood will extend from this stud right here on this edge over to here. And again, we see the staggered nailing. So here is a nail. In this case, it's coming up 2 inches. So we came up 2 inches, we went over here, up 2 inches, we went over here, up 2 inches, we went over here. And that's how these double studs are nailed. I'd like to point out that this is 15/32 plywood. That's what is known as half-inch plywood. It's 5-ply plywood, and that just means it's layered in, there's 5 layers of plywood. And this structural one is a special type of plywood that's made for shear walls. Now there's also a rated plywood that is 10%, well, it's 90% as strong as the structural one, so we avoid it. You might as well, for another couple bucks, you might as well get something that's 10% stronger, so we always do that. Now the next thing is the plywood. In this case, we're building a stronger shear wall where the nails are 2 inches apart. So along here we have 2 inches apart, 2 inches apart, 2 inches apart. Up here we have 2 inches apart, along here. Again, we have here, they're 2 inches apart. So we would go here over and then 2 inches and then 2 inches over this way, then down 2 inches over here, 2 inches. And, you know, and so we double them to the hold down. And then it's important to realize that each edge of the plywood gets nailed. So this is an edge right here. So this all gets nailed 2 inches on center. And this edge of the plywood also gets nailed 2 inches on center. So that's extremely important to remember so you don't forget to do that. And then, of course, there's the stitch nailing. So the stitch nailing that comes this way, again, we're doing them, in this case, we're doing them 3 inches on center, and I'll talk about that in a second. And then this is also really important. You see how these are nailed 12 inches apart? And so here we go, 12 inches, 12 inches, 12 inches. And the plywood, the only part of the plywood that really does anything are the edges. The part that in the center and what's called the field, we only put them 12 inches apart because they're just sort of to hold the plywood in place. And let me show you how that works. So here we have this is, you know, there's the earthquake forces pushing on this upper top plate that pushes against the top of the, you know, the plywood where all the nails are. And just figure that this plywood is just one big solid piece of wood that's nailed right here. So that when this top piece of, this big, you know, top of the piece of wood moves this way, of course this one is going to move this way. So that's actually why the edge nailing is so important. You know, it ultimately transfers down here into where the bolts are. Then these are ventilation holes. Building inspectors on building departments require that you put these in. You know, every joist, every bay. This is called a bay from the stud to the stud, or this stud to the stud. Those are called stud bays. But the only time they're really important is where the bolts are, and that's just so someone later on can take look and see if there's bolts there. That's really important for a home inspector to know that. Now, some people think these ventilation holes are important. As I said, building departments often make us put them in. But if you think about it, it's kind of ridiculous because in your garage you don't have inspection holes. In your walls you don't have inspection holes. Ventilation holes. So this is just a kind of stupidity from my point of view. They're not necessary. They're a hassle to put in. And they're just not necessary. So if you don't have some uptight building inspector looking at your work, just put them where the bolts are. Now the next thing we look at is that we have the again we have the 3 inches apart. We just looked at that, and at the double stud at the hold down locations, they're nailed with 12Ds. A 12D is a larger nail than most nails. And in this case, we're putting them 3 inches apart. Now, 3 inches apart works because it's a bigger nail than the plywood nail. And, it's perfectly, perfectly good way to do it. But in general, it's such a good rule of thumb just to say, hey, I'm just going to nail it at the same pattern as the plywood itself. So this is how shear walls are built. And when a contractor, you're looking at the proposal from a contractor and you want to ask them some good questions, you want to say, hey, where are you going to put all the bolts? And how far apart are you going to space them? And if they say, I'm going to put them every 6 feet, well, that contractor probably does not have a good understanding of retrofit engineering. They should be, every 2 feet at plywood locations because, again, the plywood is the only thing that really, all the force goes into the plywood. Because all the force goes into the plywood, only the bolts that are attached to the plywood really do anything. Now, if it's one outside the plywood a little bit, so for example, this one's outside a little bit, this one's outside a little bit, they'll still work. But in general, you want to keep them very, close together within the shear wall, if at all possible. So anyway, that pretty much sums up what I have to show you about overturning forces and shear wall construction where hold downs are involved. And I hope you found this helpful. I hope you enjoyed this video. And if you would like to hear about future videos, please subscribe. You can also email me at info@bayarearetrofit.com and ask me any question you like, and I'll do my best.